So we were at the point where the branching was correct, but the nodes were not correct. And I think what's happening, I have the feeling, might be related to docs that maybe because this whole hyper graph thingy basically is a it keeps track of nodes. I don't know how it does, to be honest. Like, do the edges have just references to the nodes? Like, I have the impression that superposition. So I have the impression that these should be done after the actual multiplication. So here I don't care because here we're just adding the node to the edge. So here we're processing the okay, but like control 0, control 1, add node to edge. I oh, wait a second. So I control node. So I'm cloning it, and I'm adding the control node to the edge. What am I doing here? So the control state is in superposition. So why am I adding it to edge 0 and edge 1? Oh yeah, okay, makes sense. Yeah, but I think this has to be just added here after I set the node. After I actually set the properties or I set the state, and I think I can just do it like this. Or let's just do it like that, just in case. And I think here processing the target is like where so I create a target node by cloning these, and then I add it to the target edge. And then I'm changing the state and all that stuff, but I think that is not what we want to do. So what we want to do is we want to add these at the end. So here we add the node to the edge. So here we add the node to the edge, and here I think that this should be added at the end, so the target node that I'm cloning, right? Because then I'm cleaning up the other stuff. So the target node I added after I've processed, because here I'm adding target node to edge 1 or to edge 0. Where's target node 0? Am I not creating these? That's a mistake. Target node. So we're adding that was a mistake. Maybe that could have been also a source of the errors. So I'm doing the dot, and then I add the node to the edge. Here I don't do anything, and I add the node to the edge. Then I do target 0, target 1 by cloning again. Now these, let's say we do also after the state modification. So we kind of add the node to the edge at the very end once we already have the new state computed. I think that's the way to go. And that should fix it. Then we remove the other ones. Now I know I might just, I could just have ignored all these because I think I mean, what I'm going to do next, if that works, is I'm going to just work on the more generic apply to like sort of a 2 qubit gate system, which is going to be based on the 1 qubit gate, but it's like a bit different. Um, it's funny that here I'm not adding, I'm just modifying, just going through the nodes and modifying these there, and that seems to just work. It seems that nodes is what holds the actual nodes, and what's in the edges is just maybe a reference or something, I don't know, or maybe it's a copy of it, I don't know. So I've done these and now I do these, sorry. Done. Yeah, no, wait a second. God, how can these not, how can these be like that? What am I getting wrong? What am I getting wrong? So I'm getting a system. I'm applying a Hadamard gate, right? I'm applying a Hadamard gate. If I draw these, then we have the Hadamard gate. Oh, that is already wrong. Oh, wait a second. No, because I'm actually creating a. I'm working with a system where, yeah, okay, that's fine. That's what this is, the plus, is the minus, because they were. So they were in a bit of a mixed state, I guess. They were in a mixed state. It was 0 and a 1. That was the initial state of the system. Oh God. So so if I now apply a control X gate, and what was the code? So this is going through the nodes, and it's giving me the UID, and then it's taking nodes and properties state and returns the labels. So if I now go ahead and I do print node labels. Oh wait, I was applying a Hadamard. Maybe I think maybe I'm stupid. Maybe that just works. So I'm getting a system. I apply the control X, and then I draw the system, and I also get the labels. Let's see what happens now. So I just literally do a Bell state now, but it's what? Oh, so what's happened here? So Q0. Let's see if I can get a better, a more clear print version of these. So Q0, they all stay in superposition, and they shouldn't. They should get split. And when they get split, they don't get the whole thing. Like the Q1 ones are also wrong. They also don't get updated. What the hell? So this doesn't seem to work. I'm literally assigning So if I just literally print dstate and then print dstate, right? Oh, actually that's wrong. Why is that wrong? Maybe now, maybe that's now for some reason not the way to do it. So stayed, stayed, stayed. What if I do like just like that? Okay, now it works. Oh, I think I fixed it. I think that's the, I guess I think that should just be a state, that should just be stayed. Yeah. And then I think this should also be stayed. I don't know. I don't know what the problem really was. If this was just, there you go. Now it's correct. So the, oh no. It's not correct for these ones. Why? ID9 and ID3 plus and minus. They should be, oh god. So those are part of the control nodes. So I'm splitting them. Why is this? I split and there's like 1, so 0, 1, 0, 1. For the control qubit. So what are we doing? So we're control node, we're cloning. Oh, and that is the problem. I gotta do that at the end. I think that's the reason. So get the edges, add edges, another edge. So control node. I'm cloning the control node, using it here, and I should probably add it to the system here. After what am I doing? I'm cloning the control node. I'm cloning these. Then I'm getting the state. So I'm calculating these. Get the edges, calculate whatever. And then I add node to the edge 1 and I add node to the edge 0. In these cases. In the case of superposition, I clone that again. Get the states done. Then add the control node. Yeah, I think the problem is that I need to add the control node 0 to the control as well, because I've just cloned it. Exactly. And in this case of 0 and 1, yeah, so this is a little bit different. So in this case, I need to add the, yeah, so I need to add these here. Need to add these here. Because the control node is both the control and edge 0, the control and edge 1. And here I need to, here I just don't add it, because what I do is I add the control node 0 and 1. exactly. Yes, yeah. Now it worked. Now it worked. Look at this. So Q0 is the control. So if the node is a 1, then it's connected to this one. If the node is a 1 here, it's connected to this one here. If it's a 0, it's connected to this 0. If it's a 0, it's connected to this 0. We have it for mixed states as well. Good. Now that we have it, let's just trash this one. Because I want to go and implement the apply multi-qubit. Apply 2 qubit gate. So qubit 0 and qubit 1 is these are the parameters. Because I think that's going to just become obsolete. This is just like it was a good exercise to get to sort of sharpen my skills with the framework. Now that I know all this stuff, I think that might be easier. So now let me just recap. Let's just remove some of the prints and stuff like that because that just bothers me. And so but we know this works, and then let's just do a simple example. Okay, so let's just stay here, and we just apply an X gate. Yeah. Where? H and X. Okay, so that's the what it does is it applies. Let's start from a proper initial state. Okay, so so I want to have create this. So I want to have get. So we want to create a normal edge here. Okay, cool. So now we have 1 is in the state 0 and this is the state 1. Why has this worked? Well, I should probably, what I want to do is I want to follow the same approach. So what I want to do really is I want to clone the node. So I want to say node equals, I think it's going to be easier if I do it this way, easier. It's just going to be cleaner. So I wanna so nodes and clone, and then I do node state equals gate, and then just like that, and then what I do is add it back. So I add it back by saying add node to edge. The edge is the qubit edge. No, so this is the node, and this is the qubit edge exactly. And then at the end, I do garbage collections. I clean up targets. Sorry, clean up the nodes. They're not needed, which is basically original nodes. So for n in nodes, remove nodes n. I'm not printing that. I'm not printing that. So I think that should still work. Yeah, perfect. Cool. If I apply a Hadamard gate, yeah, that works well. Okay, perfect. So that works. Now, I'm going to copy all these. And so how will this look like for a 2-qubit system? And let's just do go straight in Google CX matrix. So it's the matrix of control X. Control not quantum matrix. There you go. It's a simple one, I think, right? It's just a bunch of ones and yeah, there you go. So I'll add it to my collection. And I'll say, look at these. So Uh, I'll add it after the Hotmart. And I'll say that is the control node, and it's basically exactly right. And so what we want to do now is we want to have this in here, but like, so this, what am I doing? Oh, again, I have this crap. My indentation is so terrible. God. So I want to have okay, so I don't want to donate. So those two here. So basically this is what we want to have. Yeah, I needed to do that, okay? So we have the matrix without the comma at the end. So we have the matrix, and now what we can do is, and if this works, I'm just gonna kick myself because this it would have been so much easier. So for each node, right, what we do is we take a look at, so first of all, not control nodes. Okay, so yeah. I actually need to do something like that, right? And say, look, now what we first have to do here is we gotta get like, oh yeah, I already had it there. So we have Q0 nodes, and we have Q1 nodes. Exactly. So first we go to the Q0 is the control, right? So I'm gonna assume that's in the case of the C node, like that's gonna be the order. So top to bottom. Yeah. So we go through these first, and what we do next is now we iterate basically. So this is going to be actually N0. Well, I'm going to prefix everything by Q0N. So Q0N. So Q0 node. Cool. And now I go to the Q1 nodes, and this is Q1N. And so what I'm essentially doing is I'm iterating for each node of qubit 0. I'm going to iterate over each node of qubit 1, and I'll have to add a restriction here in terms of check if in shared edge. That's for later. Now we'll assume there's no edges, and so we just have one node in for each qubit. That's all good. So now we have two nodes. Now what I have to do is I have to actually get the local 2-qubit state vector, right? So the way that I do this is by SV state vector. It's basically np dot well, essentially Q0 node and Q1 node state. print SV. So this is what. So this is now the stuff that I have, and now I want to apply the operation. And so what I do is I would do so the new state vector is basically np dot, and I would just take the gate, multiply by SV exactly. So now I have SV. So this is the new state. Print SV. New SV. Cool. So now what I have to do is I have to create a branch per each of the 4 elements in this SV, right? It's cool because I think I can easily generalize that with like multi-qubit gates and then just have some sort of like an array here and just iterate over the arrays. But let's just keep it like that for the moment. So it's really this is really applying the gate, right? And now we need a loop for like amplitude in new SV, or let's put it this way. I can actually hard code these, right? Because I know the first is for the 0, 0, the second is for the 0, 1, then the third is for the 1, 0, and the fourth is for the 1, 1 element. So but how do I know? So I need to create an edge for each of the elements. Let me stop for a second because I gotta go get some coffee. Cool, I'm back. But I start to see the problem. I start to see the problem because so here I'll basically create 4 edges. Each edge will have you know, one of the nodes in yeah, so basically the way this will work is like, so I'll have edge 0, 0, right? How do I create the edges? So how do I do this here? An entity set. Yeah. So the edge 0, 0, 0 is basically new SV 0. So I'm just literally 1, 2, and 3. That's the way this will work. So I create the edges, and then I'll need to compress them. That's what I don't know how to do, especially how to go from an edge with the amplitude into separating these. But let's not give up, okay? Maybe we'll work out. Maybe we'll work out a way to do this. It's small enough that it could really work out. What am I doing? And now I need to add nodes. Yeah, and I need to basically I need to add nodes to each of these edges, and then I need to add the edges, so to say. Okay, so I'll be back in a second again. So I'm realizing that I'm actually gonna quickly end up with I think I just found the first problem with this method, which is that I think I'm not gonna find a way to work around the separability problem by doing it this way. Because at the end of the day, what I end up here with is just a bunch of edges, which still have an amplitude associated. And then if I have to figure out a way I can merge them, like I'll be able to merge them, but just assuming that I don't know, the zero nodes can be the same. Okay, but let's get it to a moment. Let's get it to a point where these are the branches that we have. Okay, so so what I do, so I would so I have the branches, and now what? And now I need to create basically these qubits, the 200 state, 01, 10, and 11, right? So I need to actually so first of all, I need to add the edge to the system, right? System add edge. So I need to add the edges to the system. I need to add each edge to the system. What? So I'm adding each edge to. Come on. You know, that's just stupid. And now I need to create. So now I need to create, basically. So I think I should just use. I should just use these. Create qubit edge. That creates the initial state. That's not what we want to do. What we want to do is we want to create node initial state and excited state. I think I should have those globally defined like these. So initial state, excited state. Exactly. And I should just call them create node initial state or excited state. So I should just say add edge. Okay, but that just gives me a no, like a node which I need to add it to an edge. So basically I'll just do no 0. No, so what I will do is I will just say system add, is it like add node to edge, node to edge, and that adds the node. And so I would now do create node initial state and edge 0, 0, right? And I do the same here. So I create n I do need to do node 0. So I do need to say, like, I don't know, P is like these. No. So P is these guy. Ugh, come on. So P is this guy. Q is like excited state. And now I need to add P, Q to the edges, right? Ooh. And I also need to add P and Q to, so P would be Q0 and this would be Q1, okay? So I need to add them to the edge qubits, right? Because those are essentially the new nodes. Yeah. So now I need to copy that for these. So in this case, P is, so this in this case are both initial state. Here's initial and excited, right? Here is, I should probably just do that in a loop. I feel so stupid. Excited and initial, and this is like that. And then we have basically P and Q being excited and excited. So this being like this edge. So I think that creates all the nodes that we need, adds them to all the edges that we need, and the edges have the amplitudes that they need. And so I think, and that's it, right? And the thing is, these probably just has to happen, like this can easily happen in a loop. Like you loop for each, and then what you're doing is you're creating, yeah, this would be the only thing that encodes where you are. Because then you just add it to the current edge, and yeah, it's just like that. So this is, I'll make it a loop. Make it a loop. Cool, how do I clean up these though now? I guess I do these. So after I'm done, I do a cleanup. So I do well, I don't need to nest it. I don't need to nest it, so I just do it like that. So this was the one. So I clean up the, yeah, wow. I don't know if this is gonna work out. So what do? We get the Q0 nodes, Q1 nodes. Then we trade over all the Q0 nodes, and then for each Q0 node, we go through all the Q1 nodes. This so far is a to-do. Then we calculate the dot product, print it. So that creates the 2-qubit state vector with dimension 4. Then we do the dot product with the gate, and then we have the I think that's not going to work. I think I got to transpose these. Oh, I don't know. Then we create the branches with the different possibilities, and then I guess after that we, not within here, but like as an outcome of these, I would have to clean, like maybe this should be always something that happens within the operations execution. Within the context of like running a 2-qubit gate, which is then I need to clean out the branches and try to find a way that I can merge them. But let's see the way, let's see how this looks like. So, if this works at all. Can this please just select stuff? Okay, CPU 11%, whatever. So we start the system, and then we apply a next gate, okay, and then we apply a 2-qubit gate. So this would be in qubit 0, and then we apply system a 2-qubit gate like this. So cool. What am I doing? Cool. So what do we expect to see after that? I don't know, probably an error. Yeah. Oh. This is obviously Q1 nodes that needs to be there. Node is not defined. Remove node. So what is it saying here? Add node to edge. Oh, here it is. What is the one that I'm trying to add? Q0 and Q1 are the ones that I need to add. Are they? Wait a second. No, I don't need to add them because I clone them so I can operate in them. I operate in them, and then all I care is about. No, I didn't. I no. I don't need to add this. Why that double click doesn't stop working? I don't know why. Oh, okay. It did something. But it is not what I expected it to do. System from state vector. Let's check step by step, okay? First of all. Oh, it's again agent. So let's just print this for a second. And then let's just comment that so far. Okay, so this is just state 0 and 0. Then we take that away. And we print after the X. Okay, so we have 1 and 0. And now, yeah, that could actually make sense. What I was seeing could actually make sense. It's just that the entanglement is not compressed yet, right? So, get it. So if I do these, I end up with that. What am I printing here, actually? That's weird. I think that's definitely wrong. I'm printing. Oh well, first of all, I need to check. I need to actually do a check. Like these things cannot be 0, right? And I think now they are 0. Yeah, they're all 0 in these branches, which is wrong. Hmm. It's actually weird. Like, what am I doing here? So, first of all, let's just print these two things as well. So 0, 1, 1, 0. And it's not the top product here what we won. Yeah, that's probably a mistake. So we just won so we won NumPy Kronika product cron. Okay, cool. Cron. Good. Let's see what happens. Yeah. Okay. So that's correct. So we get this vector, which is basically the 0, 0, 0, 1, the 1, 0, right? Should I? So what's my convention? 1, 0. Shouldn't I do this like the other way around? I think I should do Q1 and Q0 for this to make sense. What, doesn't matter? Oh, I'm stupid. I changed it in the print. So we got these and these, and then yeah, then we have like the 1, 0 state. Okay, so because I'm assuming the leftmost qubit, the rightmost qubit is the qubit 0 exactly, and so then this needs to be the target and this needs to be the control. That's the way they want this to work. And then we go from I'm just messing up with things. Doesn't matter. It it doesn't really matter how I do it. I gotta figure it. I'm so dyslexic, man. I'm so dyslexic. What matters is the fact that we go from like, so this seems to work. We go from this state to the 1, 1 state. This means the control knot has actually happened. Now, what we want to do here is also we want to know that if the amplitude is 0, it means that that doesn't exist anymore. So the edge doesn't need to be created. If where's that coded? Like I did it in the control here exactly. So if both are 0, right? So what I need to do is I need to take these from these parts. So each is it's a complex number. So okay, sorry for the interruption. I mean, not that you noticed probably, but wrong. So this is 0 and this is 1. So what we're trying to do is the probability of 0 and the probability of measuring 1. And if what it says, if p0 is different than 0, or p1 is different than 0, then we kind of calculate that. So, and this we need to do for each of these elements. Oh, no, what am I doing? What am I doing? It's just this. The probability is just the probability of measuring this basis state. We just have one basis state here we're dealing with. So, cool. And so here we do the same, but with SV1, and here we do the same, but with. So my theory is we're going to end up. So my hope is that there's going to be an easier way to keep the entanglement clean, if as clean as possible as we evolve it, by just doing cleanups after every 2-qubit operation, because essentially this will create all the branches, and then we just need to make sure we can clean them up. But this cleaning up, it's really at the end of the day the same, like it's just separability at the end of the day. So I don't know if this is going to be an easy thing to deal with anyway. I'm not entirely sure. Whether I've just kind of bumped into the same issue that we have with a state vector, where given a state like vector, you cannot easily decide whether it's separable or not. And here we have here we just have now these branches created, and because just to keep it should be easy. The problem is what happens when, as a result of that, we get into a mess with like big branches and whatnot, and then is there a way to decide whether these branches can be merged or not? Because here, in terms of algorithms, the hypergraphs, hypergraph, merge entities. Okay. So exactly. So we only do this if there's any probability, right? So the probability is different than 0. I guess that's the point. I guess that is going to lead. Oh, look at these. That is weird. So we've got just one branch with the states 1 and 1. That doesn't sound correct. I want to see 2 branches really here. I think I'm because I'm doing just what am I doing? Oh no, that's correct. That is actually correct. What if I apply Hadamard? Will that work? Yeah, actually I get these. Neat, that's nice. I get these. Look at these. Look at these. I get it. I get the bell state. That's awesome. Okay, cool. But now still the problem is going to be okay, that's easy, but the problem is going to be is how do we clean up these branches? That's the challenge. Like are we able thanks to this to find an easier way to sort of maybe there is a way we can like I'm more be more about the general case where we have um, a more complicated set of edges and we want to find whether we can merge these edges or not. Essentially, that is really the separability that we are struggling with a state vector, right? But that works. Look at the one with the one and the zero with the zero. That's awesome. That's actually really awesome. I think I'll just get rid of these. Can I get rid of these? Cell, edit, delete cells. That is awesome. So officially, these. Can we try another? Can we try another 2 cubic gate? Like 2 cubic gates. Um, I'm happy this worked. Really. Definitely need to make it a loop. What if I? So let me just comment the prints. So what if I? What happens if I start with a? I put the 2 qubits. I don't know if it's gonna work. What do we get with? Oh God, I don't think that's correct though. Is it? Probably it's correct, but we probably need to merge. We probably need to merge because here we have like a um, and that can probably be like a good use case for testing the merging because we have a branch here that's got like point 0.5, point 0.5, point 0.5, point 0.5. That's weird though. So a qubit is in the. Those are the possible combinations, right? Yeah, those are all the possible combinations I'm seeing here. Yeah, these are all the different states. Now, the question is, can we merge them, right? And we obviously can um, by just connecting. So what we need to do is we need to find, okay, within qubit 0, we have a 0 and a 0. Can we connect them? If we connect them, then we have here a plus state. And if we connect these two, we have here another plus state, right? So essentially we have end up with a plus state and a plus state, and that's really what we want. Yeah. So that we can use these as an example of collapsing, but it's just I'm afraid that these these edge merging is going to be expensive, and I don't know if it's going to be more efficient or like how do you do that? So how do you do that in with a state vector? You just do this the SVD, right, and then check whether there's anything, and you just check whether there's anything left. Like you decompose the matrix, you decompose the density matrix, and see whether you can completely decompose it as a product of two or not. So this is solvable, regardless of the efficiency. This has to be solvable here as well. I just have to find a nice algorithm for doing that. And I don't know how I'm going to play with the amplitudes in here at the edge level. But yeah, I think that's the idea. I'll probably have to go back to the voice notes where I talked about these, but I think that's, yeah, I kind of feel PT. I don't wanna get rid of these. I kind of became a bit like sentimental about my control gate implementation, but splitting nodes and whatnot, that's fun. That was a funny thing. But that's, yeah, that's basically a 2-qubit gate, and I think a 3-qubit gate could also be easily implementable. Um, yeah, can we implement a swap, for example? Let's implement a swap. What's the swap matrix? It's easy, right? Swap matrix, quantum. There it is. No, what? Come on. Oh yeah, the two ones in the middle are flipped. So if I do swap, and then you get like a 0 and a 1 here, and a 1 and a 0 here, and then a 1 here. That's what you get. So you basically, yeah. So and if I now say, well, we have a so we swap the thing. So qubit 0 should be in the 1 state, and identity should be in the 0 state. Swap is not defined. Yeah. So qubit 0, it's in the 0 state, and that's in the 1 state. Cool. And we have that edge here, which is redundant, right? Like that. Okay, cool. So it seems to work. But now what I'll do in the next video is let's just work on the compression of these edges, which is the essence of the whole thing. Is like, is there entanglement or not? Like with the state vector, you just do the matrix decomposition, the product decomposition, or whatever, SVD or Schmidt decomposition, however that's called, and that tells you this, and here we'll just have to come up with something else, I guess. But yeah, at least now I can implement generic two qubit gates, and I think I could generalize that to 3-qubit gates easily as well. Yeah. Perfect.